Hello and welcome to your video on aggregates, specifically the topics of determining mix gradations, the fineness modulus, and also understanding moisture states of your aggregate samples, which is really critical in concrete mix design. And you can see there on the screen some supporting textbook sections that support this video set. Now, before we go any further, you want to make sure that you have page 1 of the activity handout that's linked to this video available to look at and work on. So pause if you need to get that handout. Now, we want to do what's called a gradation, or figuring out what is the gradation of our aggregate. And so we actually do that using sieves. Now, what we mean by gradation is if you imagine a soil sample, you're going to have sand, gravel, all sorts of different sizes of pieces in there if you just scooped up a pile of rocky soil somewhere. And it's important to determine how the sizes are distributed. Is there a lot of the same size? Is it well graded? Do you have a lot of different sizes in there? And we also want to know how large the pieces are. Is it a sample that's primarily just really small, fine sand? Do you have a lot of larger rocks in it? And so sieve analysis allows us to do that. So the sieves that you can see on the picture here, they're about 8 inches in diameter. It's about the size of a width of a piece of paper. And they have on their metal surface, they have a metal mesh that has certain size openings. So a 1/2 inch sieve is going to have openings that are 1/2 inch by 1/2 inch square, versus number 60 sieve actually has 60 holes in every lineal inch of screen, and it just continues to grow. So 100 sieve has 100 holes, a 200 sieve has 200 holes for every lineal inch of screen. And so what we do is we take the sieves and we stack them, largest opening on top, smallest opening on the bottom, with a pan underneath. And you would put a sample that you've pre-weighed, so you know how much you're putting in, normally no more than 500 grams. And you'd pour that soil sample into the top of the stack. You'd put a lid on it. And then there's these mechanical machines you just put them inside of, and they just shake and shake and shake for typically upwards of 15 plus minutes. You shake your sample. And you'll actually get to do this in geotechnical engineering, the CENG 121 class that the juniors take in the fall. So this is how the sorting works, right? So if we had a sample that started with a 1/2 inch sieve, notice we'd put the 3/8 inch sieve underneath that, and then the number 4 sieve, which is a little less than 1/4 inch opening, the number 10, the 40, and in this particular picture they've dropped immediately to a 200 sieve, and then you have the pan below. You normally don't use sieves smaller than 200. They do exist, but there's other factors happening when you get to really tiny particles that keep them together, van der Waals forces, electrical forces, and so just shaking it usually doesn't separate them. And there's additional tests you'll learn about in soils to separate out samples below the 200. The 200 is tiny. We're talking about 0.075 millimeters as your opening size. So these are not particles that are of interest to us, say in concrete mix, in asphalt design. Clays are great for earth dams, for when you're looking for impermeable layers, but they're not great for strength for construction purposes. And normally we wouldn't want anything even below 100 sieve in any of our mixes. And so what we do though is we take what lands on the sieve and then we weigh it. So here's a sample results of a test that goes along with this sieve stack. So from the 1/2 inch sieve, I'm going to say that 0, once we were done shaking, 0 was retained. That picture shows some retained, but I'm going to say it's not done shaking and everything fell through. And then when we got to the 3/8 though, we retained 65.4 grams, the number 4, 83.4, and so on. Okay, and then you want to actually go through and calculate the cumulative amount retained, a cumulative percent retained on each sieve. And then finally, the value we really care about is what is the percent that passed through each sieve. And we use that percent passing to gather additional information about the gradation of our soil. So let's do an example. So here's where your worksheet's going to come in handy. So we have a different sample here. We have one that number 4 is our largest sieve. We go down to the 200. And on your handout, I even give you the size of the sieve opening so you have an idea of about how big they are. And then we also have the weight that was retained. So we started with about 383 grams. Then want to go through and say, okay, well, if this is how much was retained in each sieve, what's the cumulative amount retained for each sieve? What we mean by that is, say, looking at our example, what if the number 8 sieve were never put in the stack? So that 65.4 grams that was caught on the number 8 sieve would now just be sitting on the top of the number 16 sieve because it couldn't have got caught by anything. It would have passed to the number 4 and then been caught on the number 16. So the cumulative total that's caught on the number 16 would be the 83.4 grams sitting on the 16, but also the 65.4 that was caught by the number 8. What we have for the 30 is just the summation of everything above it. What's for the 50 is the summation. So go ahead, pause the video really quickly and go ahead and figure out the numbers for the number 100 and 200. And when you have those, join the video again. All right, so the numbers there for the 100 and 200 are now shown. We're at about 290 grams and 367.5 grams cumulative amount retained on the 100 and 200 respectively. The next we want to figure out then is what's the percent of the sample that was retained then cumulatively on each sieve. Now on your handout you have a formula for that. It's just the cumulative weight retained divided by the total weight. And so you can see the percentage should be increasing with each row. So pause the video and figure out the cumulative percent retained for the 100 and 200 sieve. All right, welcome back. So you should have gotten about 75.5% and just about 96% as your cumulative percents retained. This is an important column. We'll use this information, but we also want the percent passing. So how much of the sample was smaller than any particular sieve size? And fortunately, this is a super easy calc. Just subtract the percent retained from 100. So go ahead and get 100 and 200. And what you should find is 24.4% and 4.1% is what was passing. So hardly anything passed the number 200 sieve. It's a pretty large sample. And to sort of remind ourselves, if we were to look at that sieve stack, we're saying if I was looking at the second from the top sieve, what is the percent that's below, how much of it passed? So it's not just what's on one sieve, it's everything that's below that sieve. Now there's important information that we get from this gradation calculation, this gradation table, but we want to make sure we define a couple terms before we move into those values that we get from the table. So it is important when we're talking about materials for construction, we classify aggregates into 2 sizes. We classify them into coarse or fines. And so coarse are anything that's retained on the 4.75, on a sieve with a 4.75 millimeter or higher, which we saw from our example was the number 4. So anything on the number 4 or higher, anything passing the number 4 and lower is considered a fine. And there's actually a picture of the number 4 sieve with a dime on it to give you a little bit of scale. And again, though, this is important because when you get into soils, any sand or gravel is considered a coarse, and anything below the 200 sieve is a fine. Silts and clays are fines. But when we get into construction materials and designing concrete and designing aggregate, a fine is sand and a coarse is a gravel. And that's really important notation. And again, there we have the image of the opening is 4.75 millimeters. Now, that's how many openings. You would have 4 per inch on a number 4 sieve, as mentioned earlier. Now, one of the things that's going to be really important, and this is going to come back to us in concrete mix design, which is going to be module 3, but you will see this on page 1 of the aggregate chapter, is something called the maximum aggregate size. And that is the largest sieve that allows all the aggregate to pass. The largest sieve that allows all the aggregate to pass. So look back at our worksheet, and that would be the number 4 sieve. That is our maximum aggregate size for our sample. The nominal maximum aggregate size is the first sieve to retain some of the aggregate. Now, it's usually less than 10%. On our particular sample, it is the number 8 sieve, and it is 17.1%. So it's a little bit high. We may not have as nicely of a graded sample as we might like. This is the information we're going to be basing our concrete mix design on. If you were doing pavement design, there's a super pave manual, and they have slightly different definitions. The maximum aggregate size is one size larger than the nominal, where the nominal is the first sieve to retain more than 10%. So we'd still end up getting the same sizes this time, but it's a slightly different definition. We will definitely stick with the traditional definition. Now, it was important that we defined what a fine in a course was, because there's something called a fineness modulus. And you can find the fineness modulus just for your fines, right? Anything passing through the number 4 opening. And you can also find it for your entire sample, including your course and your fine. And so what that looks like is, if you were to look on your worksheet, you'll see that we have a couple different formulas. So the fineness modulus, as defined in your textbook, if you are only finding it for fines, then you actually would use any of the percent retains on sieves less than 3/8 inch, so your number 4 sieve, less than or equal to 3/8, all the way to the number 100. And you just sum up all the cumulative percent retains, and then you divide that number by 100. But notice what's highlighted on your handout. If you are using for course or the entire sample, then you always start with a number 100 sieve, and then you go up doubling the sieve size. So you'd use a 50, and then a 30, then a 16, then an 8, and a 4. Notice it jumps from 3/8 inch to 3/4 inch. This is again on your handout. The highlighted yellow section tells you use a 3/8 inch, a 3/4 inch, a 1.5 inch. So there's no 1/2 inch listed in there. There's no 1 inch, because you're only supposed to use those sieves listed in the highlighted color. So what I want you to do right now is pause the video and calculate the fineness modulus for our sample. What you should have found is that if you just added up what was between the number 8 and the number 100 sieve and the percents retained, and divided that by 100, you should have gotten back out a fineness modulus of 2.3. And typically for your fines, you would expect a value around this range from 2 to 3, and that gives you a good feel that you have a good mix within your gradation. The other way that we can look and see how our gradation occurs is by plotting the percent passing versus the sieve size opening. So you have a blank plot on your handout. So your task now is to pause the video and plot the percent passing versus sieve size, noticing the sieve size is a logarithmic scale. So make sure you plot that logarithmically. Come back to the video when you have your plot and compare it to my solution. So you should have got a plot that for the most part was a nice angular plot, but it has a little bit of a flat spot right around 50-60% passing. Okay, and so what that's telling us, and we can also see it just by looking at our percent passing or our cumulative percent passing numbers, for the most part, we're increasing by a pretty steady, consistent amount, but right around our number 16, number 30 Sieve, we have a little bit of a jump. We just go from 38.9% retained to 44% retained. So that's not a big jump like we see in other locations. And by looking at this plot, I would say this plot is kind of approaching a gap graded distribution. So there's a little bit of a flat spot or a gap in the sizes. And the way that we address our distributions is the final figure that you have on your handout. And here are 4 different distributions that you have. The red distribution is what's considered well or densely. So that has pretty much equal amounts of all the different sizes, more or less equal amounts of all the different sizes. Versus the green plot, which is gap graded, up to about 0.08 millimeters, we're pretty evenly distributed. And then after 0.12 millimeters, we're pretty evenly distributed. But in the range in between, we hardly have any samples, any soil aggregate pieces that are within the sizes in between. And so we get a flat line on our percent passing, and that's the gap. And that's why I said our sample is slightly gaply graded. The inverse of being gaply graded would be if you were uniformly graded. And what that is you have almost everything in the same size. And so you almost have 0% passing on the purple curve up to that 0.08 millimeters. But then you have a lot of sample up to 0.11 millimeters. And then it starts to flatten off again. And the final open is very much like well or densely. It's just at the top or the bottom of the curve, you're missing a certain size. And so that would be an open graded. And so these are the type of gradations. And you have your labels there on your handout. And so those are the type of gradations that we look at and why we need our percent passing so we can plot that and understand our gradations. All right, you're going to stop this video again. You have another activity to do. Complete the sketches on page 2 of the activity handout. Go. All right, welcome back. It's important that we understand the state that our aggregate can be in, from the driest state to the wettest state. And we actually have names for these states.